Hello, you beautiful people. So this is the last worksheet that I want to present to you. So we had the equilibrium reaction. I gave you the Arrhenius parameters, I gave you mole flow, I gave you starting concentration and so on, I gave you the heat of reaction and specific heat capacity, and with this I showed you in the worksheet how to construct this how to construct this diagram and how to calculate it for a continuously stirred tank reactor and for the plug flow reactor, but I showed it to you in the worksheet with the wrong inlet temperature, and your homework was to determine the volume of a plug flow reactor with an inlet temperature of 16 degrees Celsius, and for this I gave you the corresponding graphs. So as a small reminder, this is how the old one looked like with an inlet temperature of 4.4 degrees, and I gave you the calculation in the worksheet, and in the last video I showed you, okay, now we want to increase the temperature to an inlet temperature of 16 degrees, and this means that we have much higher reaction rates here. So here we had a maximum reaction rate of about, what is it, 0.6. And if we start with 16 degrees, then we can reach up to reaction rate of 1 moles per liter minute. And yeah, this is what I draw to you, the draw to you last time. Okay, let's have a look how it really looks like. So here's the enthalpy. The enthalpy balance, the red line, starting with a temperature of 16 degrees Celsius, and what you have to do right now is, okay, if you say we have a conversion of 0, then we know reaction rate of 0.7, then we go, for example, to the next point. If we have a conversion of 17%, this means we have a reaction rate of 0.5, or is it 0.35, and so on. And with this, we can construct our 1/r and conversion diagram. And if we do it for all these points, so basically here you don't have to use all the points, you just have to use sufficient points so that you can construct your diagram. And here it's not that easy to see, so this one, the last one, should be reaction rate of, let's say 0.09 or something like this. Okay, and with this we can construct this diagram. And here I showed you the plug flow reactor, which was the bad choice. So this was the blue line. There we had a reactor volume of more than 3,000 liters. And let's see if we start with the inlet temperature of 16 degrees Celsius. So this is the good choice, how it will look like. And you can see that we start with a much higher reaction rate, because 1/r is give much lower values. And then just here at the end, you get in the area of very low reaction rates. So here you have the very low reaction rates. And this means that your 1/r gets close to infinity. Okay, but how can we find out what's the volume of our plug flow reactor? So for this, we have to solve the integral, and yeah, what is it? So you can do it with the trapezoidal rule. If you calculate it, trapezoidal rule, then you will find out that this here should be a size of 2.061 if I use my trapezoidal rule. And then you can just say, okay, how to calculate it if we know these length here of this side of the rectangle, then it's no problem. We can say, okay, my mole flow at the inlet of component A, this was 1000, no, not liters, but it was moles per minute, and then we have to multiply it with the integral, and instead of the integral we can use the rectangle, and the rectangle is 2.061. the units are liter, minute, mole, oops, times the total conversion, this is 0.8, and then we will end up with a volume of 1650 liters. So this was just because I used my trapezoidal rule here with this just a few values here. If you look at Lebensspiel, so if you use the textbooks that I gave to you, Lebensspiel said, okay, the volume should be in the range of 1720 liters. So if you do it in a more accurate way, if you take more values here, especially here in this area, so you can see that we have maybe some errors here in this area. If you do this more correctly and even have here higher values, then you will end up with the volume of 1720 liters. So, but the order of magnitude is quite good. Okay, this is how you can get the volume for the plug flow reactor if you choose optimal inlet temperature. Just as a reminder, how can you determine the optimal reaction rate? If you start with a temperature that's too low, then you just have to design a bigger plug flow reactor. We found this out. If you start with 4 degrees, then you are in the range of 3000 liters. If you do it correctly, then you are in the range of 1700 liters. If you start with a too low inlet temperature, then you are not reaching the maximum possible rate. If you start with a temperature that's too high, if you start, for example, here and you would go there, then you will never reach a conversion of 80%. So basically you have to make sure that you are quite close to equilibrium, but not on the equilibrium line. And this is how you get the highest reaction rate here, somewhere in between the plug flow reactor. Okay, I think by comparing this, you can see that here you have, so the area below the red curve is much lower than the area below the blue curve. Okay, maybe just a comment on a continuously stirred tank reactor versus plug flow reactor. So normally it's if you are in the designing process of a reactor and you want to know which one is better, if you say, okay, I want to do my reaction in with adiabatic conditions because it's very easy to implement, should I choose a continuously stirred tank reactor or a plug flow reactor? And yeah, this depends on the slope of your enthalpy balance. Let's assume we start with 0 degrees, or let's say 20, and we have a slope like this. So what does it mean if we have a slope like this? So this is the temperature increase with your with respect to your conversion. So this means you have a very exothermic reaction, so this means that your reaction rate is rather high or that your CP is rather low. Then it looks like this. And if you have something like this, and if you want to reach high conversion, this means that your inlet temperature would be really, really low, so that you would have the chance to get a high conversion. So here, if you start with 20 degrees, and then you will in maximum reach a conversion of 40%. If you go to 0 degrees Celsius, then your conversion maybe go up to 50%. But you can see that because you have to lower your inlet temperature quite a lot. This means you have a very low reaction rate in the beginning of your process. Okay, the other case, what does it mean now? So if you have a reaction that is very exothermic, this means a plug flow reactor is not such a very good choice. It's better than to use a continuously stirred tank reactor. So if you have this, then you can say choose CSTR. So for a CSTR, maybe if again you want to have a conversion of 80%, then you just say, okay, I need this, and if you want to operate this, then you just have to make sure that the temperature inside your reactor is about 60 degrees Celsius. So basically this would mean that you could also start with a very low inlet temperature, but nevertheless you still have the high reaction rate that takes place everywhere inside the reactor. So for a very exothermic reaction, choose the continuously stirred tank reactor. If you have it the other way around, if you have something, for example, like this, so this would be how to say this, little exothermic, I just call it little exothermic. This would mean delta R is low, but it's still positive, still negative. Or this could mean that your CP tilde is very high. This could mean you have a lot of inerts in your system. So no matter how high your conversion, your temperature increase is not that high. So this is meant by little exothermic. So if you do it like this, then you will find, okay, the best way is to operate here, choose PFR. So what's the reason for this? If you have a look here, you can see that that your reaction rate reaches here in between. Here you have a high reaction rate. This means your reaction occurs faster, whereas if you choose continuously stirred tank reactor, this would mean that you only have your reaction rate of 0.4 everywhere inside your reactor, and if you go for the plug flow reactor, you would have even a reaction rate of 0.7. So if it's little exothermic, plug flow reactor. If it's very exothermic, use the continuously stirred tank reactor. Okay. Then the part B of your homework was the recycle reactor. And for the recycle reactor, there was given the reflux ratio. So we had a reflux ratio of 0.82. And if you remember, let me see. So if you want to know your inlet conversion, then I think I gave it to you in the last, worksheet number 5. So this is just the recycle ratio divided by R+1 times the conversion at the outlet. So if we put it in, then it's 0.82 divided by 1.82 times 0.8, and this here is 0.45 times 0.8. Then you have a inlet conversion of 36%. So what does it mean? our plug flow reactor, our plug flow reactor that has a recycle stream. So here you have the inlet, there you have the outlet, here you have the recycle flow. Holy moly. So R is 0.82. Here you have the outlet, here is XA, here is XA in. This means that our inlet conversion to the plug flow reactor or to the recycle reactor this is 0.36. And yes, what does it mean in our conversion temperature diagram? So this means that we are still on the enthalpy balance. So this is an adiabatic system. If we know the inlet conversion, then we also know the corresponding temperature. But so the reactor just operates in this range here. So we are starting with the inlet conversion of 33%, and then here's our outlet conversion. XA is 0.8. So this is XA in 0.36. And so this means we are just operating in a temperature range of, what is it? Something like 42 degrees up to, I don't know, 67 degrees or something like this. Okay, and now again, how to construct your diagram. So basically you are just using these points here, and these are the same points that we already had before. So we can use the same 1 over R XA diagram, but so we just have to make sure that here we have our XA 0.36. That's why I wrote it here, inlet conversion. So this is the value here. And yeah, what do we have to do right now? So this is the formula how to obtain the volume for the recycle reactor. So you have to rewrite it. So the volume is n dot A0. So the volume flow times the inlet concentration is the inlet mole flow times R plus 1. And then you have the integral from 0.36 up to 0.8, 1 over R dxa. Okay, this means we need now, we need this, next try, we need this area here. Okay, and there I looked up what Mr. Levenspiel said about it, and he proposed that an area like this, this should be, if you take 0.5 here, then everything should be fine. So if you, this would mean that this area here should be the same as this area. Okay, if you look at my red line here that I just draw by hands, then it's not such a good agreement, but I trust Mr. Levenspiel that he had a good idea on this value. Okay, and then let's just put in the values. The mole flow was 1000 mole per minute. R plus 1 is 1.82. And then we have the integral here, and this can be calculated as a rectangle. So this is 1.5 liter minute per mole times, and now we have to use just the basis here. So, and this is 0.8 minus 0.36. Okay, and then we can type it in, and if we do it, then we end up with the volume that is, so it's not exactly, but it's almost, then I have a value here of 1,200 liters. Okay, basically that's it. And so what's from my point of view, what's quite good about the plug flow reactor is that, so normally you would think, okay, we have the continuously stirred tank reactor as one extreme, and the plug flow reactor as the other extreme, and the recycle reactor is always a compromise between the two. But here you find that the recycle reactor for adiabatic operation has the lowest volume. So the recycle reactor basically is the best one that you can choose. Why is it the case? If we go back maybe to this diagram, then then you can see that you are skipping out all the areas here with the low reaction rates. So here your reaction rate is rather low. You would start at the beginning of the normal plug flow reactor. You would start with the low conversion, with the low reaction rate, and this is skipped here all the time. You are starting with the reaction rate that is about 0.7, and then it's decreasing all the time. So it means you are leaving out all this area here. So this you don't have to take into account, and this makes your reactor smaller. Okay, then maybe as a summary, let's write down all the values that we had. So the best one was the optimal path, where we said, okay, we want the temperature to vary all along the plug flow reactor. There you had a volume of 408 liters. Then if we go for the recycle reactor, it's really a pleasure today with this pen. There we had a volume of 1,200 liters, so it's nearly 3 times the minimum volume. Then we could go for the plug flow reactor with a good inlet temperature. So if we choose 16 degrees Celsius, then we need a volume of 1,720. Let's take the values from Mr. Levenspiel. And if we say we take the continuously stirred tank reactor with 4.4 degrees Celsius, then we have a volume of 2,000 liters. And the last one was the plug flow reactor with 4.4 degrees Celsius. There we had a volume of 3,032 liters. So you can see that this one, if temperature control is not a problem, then this one is good. And if you want to have it adiabatic, so then you can see that this is here a quite good idea to use a recycle reactor. Okay, so what is missing? So we didn't talk about PFR with intermediate cooling. and we didn't talk about tank in series. With intermediate cooling. With intermediate cooling. Okay, since we are running out of time, I will not present this to you, but I think it should be quite clear how to construct it. So you just you make a break in your reaction, you change the temperature, and then you again run you're constructing your 1/r diagrams and so on. Okay. Yeah, maybe some last words about the corona simulation. So we started with the corona values, and what I expected from my simulation that after loosening the lockdown measures, I would have expected that the infection rates would increase again, and that like right now we would have some daily new infections, about 1,000 cases or whatsoever, or even more, maybe 2,000, 5,000 daily new cases. And what has happened in the last days? So if you look at this, so even though I don't know, here somewhere in this area, we decided to open up the schools again, you can go shopping now and whatsoever. So the corona cases are not exploding. We don't see any exponential growth, but this is all very, very limited. And luckily I was wrong. And what you can say is that the measures that were taken, so the control of the health, what is it, Gesundheitsamt, the health authorities, that they have a good control of maybe people who might have an infection, about the decision on quarantine should be really good. And what you can also say this is that this very simple device of your mouth and nose protection seems to be quite good. So we had the effect of the lockdown here, and since then we have no really increase of the rate. So it's all, or I modeled it with the reduced rate constant, and this rate constant hasn't changed so much. I think you remember this. So this is the total cases that we have so far. These are the closed cases, and here the green ones are the active cases. So, and right now there are only, I don't know, less than 1,000 active cases right now. So if you look at the daily new cases, I took it from different sources. So this is Robert Koch Institute, this is Morgenpost, and this is the Zeit, the German journal Zeit. And here you can see that this is at the beginning you had the exponential growth, and then I just modeled a change of the rate constant once, and with this the agreement is rather good, I would say. So if I should interpret it with the chemical reaction view on it, then I would say, okay, the reaction rate of the coronavirus is still very low. If we zoom in here in this area a little more, then you can see the blue line is my simulation, and the values that you can find are all around this blue line. So everything is basically as expected. So this means, luckily, we don't see any negative effect of the loosening of the lockdown, and I really hope that it will stay the same, and that we will come across the summer without a strong increase of the new infections. Hopefully we can see each other again in the winter semester and the winter term, so that we can have personal meetings with on our lectures. Okay, thank you very much. All the best for the exam, and yes, thank you.